Hi, and welcome to the very last integration video. Well, actually, this video has been broken into two parts. So there's two, this one and one more to go. But this is on the same question. And we've broken it up into two videos because we can't fit the whole question into 5 minutes. So please make sure you've got at least 10 minutes up your sleeve before you sit down and watch the last two videos, which is this one question we're going to look at. All right, remember we've talked about these different types of differential equations that exist. We're going to pick on one of these, probably the hardest one, and show you how it works in a word-based question. All right, here's our example. The population of New Zealand is growing at a rate that is proportional to the number of people living in New Zealand at that specific time. Now that kind of makes sense. In other words, if we don't have a lot of people in New Zealand, our population is not going to be growing at a fast rate. But the more people we have, the faster the growth rate would be. Okay, well, we know some facts. The population was 3,916,000 in December 2001, and the population was 4,209,100 people in December 2006. So we're going to write a differential equation, determine the particular solution, and use it to estimate the population of New Zealand in December 2025. Right, because we were told that the population is growing at a rate that is proportional to the number of people living in New Zealand at that specific time, when we look at our four types, we're talking about the last example, where dy over dx is equal to ky. But we're going to write dp over dt is equal to kp. Now p is the same as our y value, but we're going to use p for population instead of y. dt is like our dx, but we're going to use t for time. And the k is the constant that we need to have. If the population was decreasing, we'd just change it to say dp over dt is equal to negative kp. That's all we'd do different. Right, let's find our general solution. So we're going to use the technique of separating the variables. We're going to take the dt and times it on both sides to get dp is equal to k times p times dt. Now we're going to divide by p, so we're going to end up with dp divide p is equal to k times dt. We're just going to write the left-hand side as 1 over p times dp. Right, now we'll do our integration. So we're going to integrate the left-hand side, integrate 1 over p with respect to the p variable, and we're going to integrate the right-hand side, which is k, with respect to the t variable. Right, I'm just going to write this up here so we can carry on our working in the next line. Okay, when we integrate the left-hand side with respect to p, we're going to end up with the natural log of p. 1 over p integrates to natural log of p, plus our constant d. When we integrate the right-hand side, k is just a number, and we're integrating it with respect to t. If we were integrating with respect to x, we'd get kx. But because we're integrating with respect to t, we're going to get k times t. So just think any number integrated with respect to x becomes 4x. But if it's 4 dt, we're going to get 4t. So if it's k by itself, it will become kt. Now we're going to put the two constants on one side and call it c. Okay, now's the tricky bit. We're going to take the e to the power of the natural log of p on the left and e to the power of kt on the right. Now, why did we do that? Because e and natural log are like opposites, like squaring and square roots. So they cancel each other out. So what that gives us on the left is just p. And on the right, we've got e to the power of kt plus c. Right, well, this is our general solution. We're going to use that to go on and find a particular solution in the next video and solve our problem. So please watch the next video right now.